I realize I'm standing between you guys and lunch. You're standing between me and my afternoon nap. Very jet lagged, so ask questions won't be hard to confuse me. All right, so I'm going to talk to you about at least some of the aspects of why I'm optimistic about silicon photonic quantum computing. I'm going to focus on the theory stuff. You all here in Bristol know photons well and why photons are good. They like to travel around. They have minimal decoherence. They have high fidelity optics. This is a picture of one of the Bristol Photonic PhD students. It's what comes up when you Google it. But the bad thing about photons is that they travel too fast, okay? And they get lost, like this guy. And then the really ugly thing about photons is that they don't interact well with other photons. So as soon as you have two photons that are distinguishable, it's hard to see this, they start not playing together very nicely. And so building a quantum computer with photons, it has had many pessimists over the years. And there's sort of many, I guess, legacy misconceptions about photonic quantum computing. Things like it's not scalable, there's no real architecture, you can't get around loss, the gates are probabilistic, the scaling isn't good, and so on. And things like you need a quantum memory. So there's many of these things that have taken us years to work through to get around. If you're an optimist like me, what you want to, your basic response to this is, yeah, that might have been true, but now it's just wrong. Okay. But it takes a lot of work to kind of go through and sort of examine all this in detail. So rather than sort of go through all of those kinds of things in detail, I want to focus on the reasons to be optimistic. And the sort of key reasons I think that are critical are the following. It's possible to do everything for photonic quantum computing in CMOS compatible processors. Now, it might not be the best way of doing sort of individual components, but given that these components then become manufacturable, we focus on doing everything in CMOS type processors. Okay. The other thing about this architecture is that it's very modular, and in contrast to matter-based approaches, which start with small numbers of qubits and then sort of face the problem of how do they build the bigger device, this architecture, the hard part of the architecture is actually just creating small entangled states of a small number of photons. And then the components that go into making that are in fact more difficult than the components that you need to scale the thing. So the scaling part is sort of essentially, from a theorist perspective, solved once you can build these small photonic entangled states. But the main reason I'm optimistic is that I think that this is the only platform that can seriously stare down the numbers that you require to get fault tolerance, to get genuine fault tolerance. And what are those numbers? Well, I think everyone who's thought hard about actually building a quantum computer agrees on the following. This is a figure from Google. It came out a few months ago, they put on a blog. And it's basically, here's where Google are now, sort of at the border between classically simulatable and then there's a question mark here saying, near-term applications. So there's a lot of hope that maybe we find something around the 10 to the 2, 10 to the 3 qubits at some, not too crazy low noise rate that actually makes the device useful. But there's a question mark there because no one really knows of such an application, right? And I wouldn't want to gamble my life on it. I'm not gambling my life on it. But the only thing you really can sort of state with surety is that if we can get to around 1 million qubits and some reasonable noise levels, then we can do useful things. Right? And 1 million qubits is a lot of qubits. Right? It's a number that you look at, and this this number keeps me awake at night. I really want to make that number smaller, which you can do. Unfortunately, it's not quite that easy. Okay, so this one keeps jumping. So the key challenge to hit fault tolerance, I think, is that you need components, manufacturable components, because to stare down a number like 10 to the 6 qubit, you're really staring down tens of millions, possibly 100 million actual components in your device, right? And we're not talking trivial components. We're talking about things that do stuff and that function. And the only way humans have built anything that can stare down tens, hundreds, billions of components is with CMOS compatible processors, right? That's how come you have a phone in your pocket today. So the reason we focus on those kinds of processors for doing silicon photonic quantum computing is purely because that's the only way we can see to hit fault tolerance. Okay, it's not because we like them or think they're fun. Okay. Now, what are those components? After I've had my nap, Mark will talk to you in more detail about silicon photonic components. So I'm just going to skip over it fairly quickly, but basically, in our architecture, there's two types of photons. There's photons that become qubits, and there's photons that are sort of part of preparing a large entangled cluster state. But roughly speaking, we need detectors to herald single photon sources. So we use sort of nonlinear processors to produce single photon sources and herald them. We need delay lines because the photons travel too fast. We need switches to multiplex them. And we need beam splitters, like very simple interferometric gates. And those are the components that we have to manufacture, and we have to be able to manufacture at scale. There's no point being able to manufacture all but one of the components if you want to try and make 1 million qubits. Now, the photons that are part of the final, and I should say that the critical thing about this architecture is that as you scale the computation, as you go to larger and larger algorithms, the depth of the photon world line stays constant. Okay? It's not that you have to send the photon through more and more devices as the computation gets bigger. And that's critical because loss is going to go sort of, scale with your number of devices. Okay, so the photons that are part of the readout, they basically just have a single measurement performed on them. They essentially get asked this sort of existential question that's captured in this cartoon, which is, I don't know whether I'm a wave or a particle. And so you ask every photon in this device, are you a wave or are you a particle? So our qubits are actually just a photon that's in one of two waveguides. And a computational basis measurement is just asking, are you in this waveguide or in this waveguide? It's like asking, are you a particle? And the X basis measurement, the measurement in the plus minus basis, is do a beam splitter and then detect them. And that's like asking, are you a wave? And so every photon, like out of all these millions of photons, they all actually just get measured in the X or the Z basis. And only three things can happen. We detect the one photon and nothing at the other waveguide, or we get the other thing, so we get one on the left, say, none on the right, or one on the right and none on the left. Or we detect no photons, or we detect two photons, we get some kind of error. And so we have a classical readout here that goes off to a classical computer that just says, I did the measurement in the Z basis, for example. I measured that photon and I got this outcome, or I saw an error. Okay, and the error is loss and so on. So there's this small amount of classical information that has to go off to a classical controller who does the decoding for the error correction. Okay, and then another photon comes through. The choice of measurements for the photon immediately after this does not depend on what goes on in that classical controller, which is good because these photons are coming too fast. Okay, so that's the sort of the rough set of components, and Mark will talk to you about most of those components in silicon photonics. But we are interested in fault tolerance. And fault tolerance is not, like at Christmas you're like, yeah, we tolerate Uncle Bill's faults, things will be okay. Fault tolerance is also not, well, we just got low error rates and maybe we can run some kind of thing that has some noisy algorithm and maybe get some answer that's approximate. Okay. But fault tolerance is also not, and I think that this is something that is understood, it's not error correction either. Okay, error correction is an amazing feature of the world where you can encode a qubit in a large entangled state of many qubits, and then you can determine what errors have happened on it. Okay. But there are plenty of ways of doing error correction, most ways of doing error correction that are not fault tolerant. Okay. Fault tolerance is an extremely challenging thing. Fault tolerance is saying everything I do has to be noisy, and yet I still have to be able to do the computation. Everything that does the encoding in my error correction, the readout, everything has to be able to tolerate noise. Okay, and error correction is not good enough for that. So to give you an example of sort of fault tolerance in a matter-based architecture, this is a diagram that's based on the phosphorus and silicon type architectures, but it's exactly the same for superconducting qubits. So to get fault tolerance, you have to say, I'm going to let everything be noisy. So in this particular architecture, which is based on the surface code or the toric code, you have some data qubits, which here are black. You have some ancilla qubits that are ancillas that you use to do parity measurements, so what we call stabilizer measurements in either the Z or the X basis, and they have to be included here. Okay. And then you have to do, so you have this particular error correcting code. It doesn't matter if you don't know the details of it, but you have to follow it. They have a sort of schedule of interactions between these ancilla qubits and the data qubits, and they have to follow this circuit. So in this case, it's sort of multiple gates that go around that entangle the ancilla qubit with the data qubit, and then lets you do this parity measurement. Okay, and so you've got this sort of loading and unloading of parity measurements and these scheduling issues. And fault tolerance is about everything here being noisy. Okay, all the ancilla gates, all the everything that's going on being noisy, and yet you're still able to compute. And I think it's an amazing feature of the world that we can actually get fault tolerance. And for this code, you can tolerate sort of on the order of 1% or 2% of stochastic noise and still do quantum computation. Okay, so in the photonics case, we are not going to follow this particular way of doing it, but I put it up there because I'd like to sort of emphasize a distinction. So in photonics, the way we're trying to get to fault tolerance is we want to build an entangled state. So this is a cluster state. Okay, so it's an entangled state of many photons. You can just think of the bonds as some kind of entangling operation, and the circles are photonic qubits. Okay, and by comparing it, so the way to sort of understand this is, think of this. I mean, unfortunately, the colors don't match up, but that's because I didn't draw the previous diagram. Think of this line here as like one of the data qubits in the previous slide. Okay, like a black line here. And what the ancilla qubits did was they coupled sequentially to these data qubits to do a parity measurement. And in this figure, that's like one of these ancilla qubits. Okay, so you've got a data qubit going up, so think about time being in this direction. I've got a data qubit here, another data qubit, another data qubit, and then I have the one sort of sitting in the face there and the face here. These are like the ancilla qubits. But you see that physically, it's all just the same thing. There's no distinction in actually how we're building it, it's just the same cluster state. So there's a certain homogeneity to the whole thing that says, okay, we have to hit those noise thresholds, but we don't have to sort of have this like actual architectural distinction as we build this thing. Okay. These are all just sort of identical qubits. Okay, now we would really have a lattice of these things. So here's a picture of, thousands of such qubits. Now I've put kind of time going this way. And we make measurements like this in time, and it mimics that sort of 2D matter-based architecture. Okay. So I don't know if this will work out. Here's an animation of it. But if you look in this animation, what you'll see is that I'm not actually producing that ideal lattice. Okay, I've got this lattice here, so these are our entangled qubits, but there's sort of holes in it, things that are imperfect. Okay. And so a big part of what we do is we try to understand how to make this lattice better. So we make it, the reason it's got holes in it is that we actually start from very small entangled states. So this is from Mercedes Jimenez Segovia's thesis from a few years ago, but there's many different ways of doing this kind of thing. You start with small entangled states, and if you can produce these small entangled states, then you can, just using beam splitters, you can fuse them together into this kind of thing, into a lattice like this. Okay. And then if this lattice is good enough, you can hope to get to fault tolerance. Okay. Because we're sort of building in the fault tolerance into the specific entangled state that we're producing. So there's many different initial states that you could use as your initial entangled states, many different ways of putting them together. Okay, here's a sort of diagram that looks at the site probability on the lattice, so whatever particular lattice you're looking at, what's the probability of qubits there, the bond probability, which is the probability that you have entanglement between that qubit and the ones around it. Okay. And what you find, and you should just think this is just a heuristic, think of this as a heuristic diagram, is that there's some region in which the lattice that you produce is computationally universal. That if you have enough qubits in your site and enough bonds, then you can do universal quantum computing. Okay, this figure's sort of out of date. We can actually do it with just 2 qubit entangled states we can get in this region now. But what we try and do in the theory side is to move this region this way. So this is the sketching for the surface code lattice. There's other, we have better codes that have other regions. But computational universality is still not fault tolerant. Okay? The reason, so with computational universality, you could say, well, you could build a universal, a fault tolerant state, but the process of doing that actually amplifies errors. So there's a different region on this diagram that I haven't plotted, which is the region at which we go directly into a fault-tolerant code. If we produce this particular cluster state and we have a dense enough sites and dense enough bonds, then we just get fault tolerance for free. Okay, we're there, we're into this code, we've made a transition, it's like a phase transition. Okay. So we spend a lot of time trying to take different particular entangled states, finding codes where this region gets bigger and where the fault tolerance region gets bigger, and then get ourselves sort of directly into a fault tolerant code. Okay. And I said that there are codes which are better than the surface code, than the Tori code. There's a code that was found by Naomi Nickerson very recently, sort of based on this funny looking cluster state. The nice thing about this code is that it has erasure thresholds of better than 50%, which means that you can lose more than half of the qubits in that state, and you can still be fault tolerant. It's got Pauli error rates of pushing 10%, whereas surface code is sort of 1 or 2%. So, one of the reasons I'm optimistic about this game is that the challenge is very clear. It's like, make yourself some small entangled states and then get into this region, and kind of everything else should be okay. Okay, so the other thing that I wanted to say about this code is it shows really a fundamental difference between cluster state quantum computing and kind of 2D matter-based approaches, because this particular cluster state, you can't think of it in the way I just explained that 3D lattice to you, where I said, oh, just think of it as time slices of the surface code, of the toric code. This is really a fully topological 3D object. So I actually think that some of these results that are coming through on cluster state codes will suggest that even architectures that people now think of as circuit-based will switch to being cluster state-based, just for fault tolerance reasons. Whereas in photonics, we're kind of forced into cluster states just for sort of resource reasons. Okay, so the big challenge, or let's say a challenge that we didn't know a few years ago whether we could face it though, was whether our classical computation could actually handle the protocols for dealing with all these measurement outcomes that are coming out, very fast, at sort of maybe a gigahertz or so, in order to run our error correcting codes and so on. So you have this kind of process that goes on where you have the code, you have this big entangled state. Now you do these measurements that basically tell you about potential errors in the system. That has to go into a decoder. The decoder then sends back some information about the sort of encoded logical gates that you're going to do. Okay. And the issue is that you many people have identified this, and there's some great talks and papers by Austin Fowler on the Google approach to this. But you can very easily run into a problem where you kind of have a backlog in your classical computation. And this is one of those things that it sounds like, oh well, classical computing can be arbitrarily fast, but it can't really. And for photonics, this was particularly a potential issue. So to give you some sort of numbers, so here's the sort of loop where we do, between our quantum processor and our decoder. And so sort of based on these various papers, roughly speaking, if you're doing stuff with, say, NV centers, well, you have a long time to do your decoding, maybe 10,000 nanoseconds or something, right? With trapped ion, 10 million nanoseconds. And in trapped ions, you might have thousands, right? But with photons, we're looking at sort of around 40 nanoseconds of time to do this classical processing. And so this was quite problematic, because even though to a computer scientist the algorithms for doing this decoding were efficient, in practice they were, they sort of took cubic time. And so we found, when I say we, this was Nicholas Delfos and Naomi Nickerson, found an effectively linear time decoder that works for the surface code and works for these new families of codes that have been discovered. And because it's effectively linear, it doesn't, the nice thing is that it doesn't sort of reduce the threshold for fault tolerance too much. And we've been looking at putting that into hardware, and we can get sort of well under that 40 nanosecond issue. That was an obstacle for us. So I focused on fault tolerance and not on devices and so on, because, as I said, Mark's going to talk to you a bit. But that's the sort of summary of the reasons why I'm optimistic. It's not that I think anything is guaranteed, but I think that if you want to be serious about fault tolerance, you have to, face down some numbers that are pretty scary. Okay, and the only way I can see of doing that is with these processes that we can sort of manufacture in the standard foundry. Okay. Now, because there's some theorists around, there's sort of a whole bunch of questions that we work on. Some of them are just pure engineering questions. Some are kind of more abstract. These are sort of more engineering theoretical questions, but I think there's actually very interesting questions. At the moment, we force photons to be qubits. They want to be higher dimensional objects. We should find things that do quantum information processing more naturally with higher dimensional objects and so on. So my sort of final summary of why I'm optimistic is that I think with photons, we have low stochastic error. We have CMOS compatibility. Every component can be done in the CMOS process. Not yet as good as we like, but in principle can be. And the fact that our challenge is small in some sense. We just have to produce some 3 photon states or some very small number of small entangled states, and then after that we just send them through beam splitters and potentially get a fault-tolerant cluster state. So I'll leave it at that. Thank you.
Questions?
So I got 2 quick ones. First one, you mentioned that you want your photon to go through and not have to go through more components as the size of the problem scales. But you got to go at least have a logarithmic growth, right? Because you need your photons need to be entangled across the entire.
That's absolutely critical that is not true. So in fact, you can lay it out. So this is a schematic of a 2D layout where, so every black dot here is a 3 photon source. They just go into beam splitters here. This one goes into a time delay, and they only locally, they go into a time delay so that I can produce some entanglement in time as well as in space here. And every photon, let's say it comes out of the source, it goes through 1 beam splitter. So it basically goes through as many components as it takes to produce the 3 photon entangled state. And then the computation scales with the size of the cluster state in width, but the world line of the photon stays constant.
Okay. And then you said that you can do, you can lose more than 50% of your photons, but then how can you prevent...
A code is not a state, that's the
but how can you prevent branching your computation into 2 identical computations?
The answer is then, this is something that we had a whole discussion for a day. It's very confusing. The state is not a code, and so the state can lose more than half of the qubits. It's still something I find confusing. Hector Bombin and Naomi and I argued about it for a day. There are states where you can lose more than half of the photons and still have your encoded qubit and still do lots. So Crazy Graph is one that I wrote up in a paper somewhere, and still do universal gates like logic gates. And then if you do this kind of funny game of you give half the qubits to someone else, they essentially the state forces them to only be able to clone in 1 basis, and it's sort of it is weird, and I still find it confusing. So as you can tell.
Other questions?
Cool, thanks for us. So the surface code, I guess, solves kind of random Pauli errors, right? But what do the errors look like in photonic qubits? And more specifically, what does the error of either dark counts or distinguishability look like?
So there is no, remember that at the end of the day, what goes to this classical controller is just I got outcome 0, outcome 1, or +1 or -1, or I detected an error. And it's not actually possible for any of those other things, for anything else to happen. So the only thing that the decoder can interpret something as, in the way we've specifically constructed it, is as Pauli error. And all of those things just become some kind of increase in some correlated, potentially correlated Pauli errors. And so that's what we simulate, but it doesn't matter whether it's dark counts or distinguishability or whatever it is. Essentially, the code, as long as that rate is below be, and we want to operate well below threshold. But as long as that, whatever that rate of stuff is, so as long as your dark count rates are, are below 1%, and as long as your distinguishability is below, and as long as the sort of addition of all those things pulls you within the threshold of the code, then that's the magic of error correction.
Can you say something about the requirements of the delay line, and does that delay vary with the size of the computation?
No, it's not a memory. It literally is just a delay because the classical stuff is too slow. Basically, it's just put the photon in. I mean, Mark, I guess, might talk a little bit more about that, about the actual delay lines and sort of, and that's actually one of the components that does not keep me awake at night. Pretty much every other component does keep me awake at night. But yeah, we just put them in the spiral. They can go around, they can come back, and by then we know what we're going to do with it.
I got time for a few more questions. Alex?
Do you have any requirement on any number resolution in the detectors? And if you did have number resolution, would it help you out?
So, number resolution. I mean, so the way we're looking at doing it, you can get the number resolution by just fanning out multiplex and cascading beam splitters. In fact, like if you pump your sources at a low enough intensity, you don't even need number resolution to herald. You don't even need a very efficient detector because what matters is the conditional probability that when you think you have a photon, you actually do, okay, and that you have one. So, if you were pumping, and we wouldn't pump this low, but let's say you were pumping at a probability of 1%, then you have a 1 in 10,000 probability of 2 photons. The point is that those 2 photons can only lead to a Pauli error. Like, whatever it is, even if they get all the way through without causing something else detectable, at most they can lead to a Pauli error, and that 1 in 10,000 is way below the threshold. So, that in this game, you basically have to decide. You don't polish the firewood. You don't make stuff better than it has to be. So, hang on, is that what you asked? So you asked?
Yeah, if number resolution can help.
Oh, so whether it can help. So it would, if it was good enough, be able to, at sort of more intermediate stages where we make some of those gains, if we had good number resolution, it would be good at like kind of reducing the sort of footprint overall by a lot. So, yeah, we would like that.
All right, it's time for one more question. Any more questions? All right, lunchtime. Okay. Thank you.